Okay, so this is actually a product. We call it a product, software as a service, if you want to call it that. It's called Hopsworks. Those of you who don't know what hops are in English, it's that little thing up here. It's a plant. It's the main ingredient in beer. Auf Deutsch heißt das Hopfen. And Hopsworks is the place where you make beer, which is where we are now, which is a brewery. So we felt it was very appropriate to launch Hopsworks in a brewery. Okay, that went flat, like beer, like bad beer. Okay, but we're going to talk. Part said it'll be about Flink. It's not. The talk isn't. The main part of the talk isn't Flink. Okay, it's really about this platform for managing data. How do you manage, curate data, and how do you do then analytics on that platform? And we're going to talk a bit about the platform. And in particular, I'm going to talk a lot about multi-tenancy and metadata in the platform. So the thing is, it's a new platform, and like Para said, my name is Jim Dowling. I'm a professor at KTH. That really doesn't mean anything. If I tell you this is a cool product, you know, that won't really work out. And I had a conversation with a guy from the Netherlands over lunch, and he was telling me, in Germany, the most important thing is that you have a figure of authority who tells you that this is good. So maybe it's Testbericht or someone like that. So I said, okay, let's get someone. We have a figure of authority. Here we go. Our first user of Hops. If you don't know who it is, it's Leslie Lamport. He's the inventor of the Paxos algorithm. And yeah, so he's one of our main guys. So if you don't believe me, Leslie might tell you. Okay, but I'm going to talk about multi-tenancy in Hadoop as it is today. How we do multi-tenancy. We also support some other systems on our back end, like free text search of Hadoop in this Hopsworks platform. And then finally, I'll talk a little bit about Zeppelin and Flink. And in the middle, I'll just kind of hop over and back to a demo. I think it's I might leave the demo until the end, because if I flick over and back, I've noticed that the screen takes about a minute to reset itself. So I'll leave the demo until the end. Okay. And just shout a few questions, right? This should be quite interactive. So if you want to stop or ask anything, just shout. So this platform, I said multi-tenancy is an interesting problem. This kind of came from a European project I coordinate, where we're trying to support medical data and genomic data in Hadoop. And one of the problems you have is that if you have studies in clinical setting, or if you're in projects in a company, if you have different departments, different organizations, and they're starting up their own projects, you can have an individual here who's a member of multiple projects. And in Hadoop world, if you're a member of multiple projects, you're still going to have the same Kerberos identity. And what you'd like to do is you'd like to prevent, for example, somebody copying data from this project to that project, or cross-linking the data. So this is a kind of, you know, if you have an individual in an organization, they may be in one project, but you don't have control to make sure that person isn't in another project. And then you get into issues of, okay, well, we have roles for individuals. I have a role for an individual when they're in this project, and maybe a different role in this project. If you get into advanced security, you get into this issue of what you call dynamic roles, that, well, when I'm in this project, I shouldn't be allowed copy data in here, and you get into quite complex security rules. But this is the general idea of what we want to do. So what we want to do is be able to take a big Hadoop system, break it down into projects. And when I say projects, I think of things like GitHub, right? You have lots of different projects in GitHub. And we don't want people to be able to copy data across projects. But what we still want to be able to do is have data sets in projects and share them. Because it's not much good in Hadoop if you have data sets and you can't access them from different projects. So here we might want to say to NSA, yes, you are authorized access to our data set. And by sharing data, we don't mean copying data, we mean just linking in data. Right? So sharing by copying is a cheat. It's not really much good in a big data world. Okay, so let's think about how we do that in a database context. So I'm assuming now a basic knowledge of databases and relational database terminology. But we have a database, and we have two users, Alice and Bob. And we imagine two databases, DB1 and DB2. They could be our two projects we just introduced earlier on. And if we wanted to isolate those two databases from one another, we can write the following, yeah? This is pretty straightforward. Grant all privileges on database 1 to Alice, and grant all privileges on database 2 to Bob. So this is something I do all the time in MySQL. You can add a password at the end if you want, if the user doesn't have a password already. But you can go even more fine-grained in MySQL if you want to. You can say, for example, grant select privileges on DB2 and on a particular table. You can even go to the column level if you want to for Alice. And then you can even restrict the IP address from which Alice can issue those queries. So you can see that access control in databases is pretty straightforward. We have these things called privileges, and we can have them at very high levels of granularity at the database level and then at more fine-grained levels of granularity. Now, what is great about databases at this level is that what happens if I remove, for example, this table here? What happens to the privileges with that table? So I call drop table db2.sensitive table. Anyone know? The privileges disappear, don't they? Automatically. Why? Anyone know? Shout out. Sorry? Well, it depends on your system, but typically in your information schema you have foreign keys that will drop them as well. It depends on your database, of course. But the point here is that you can, typically in your information schema, you might have a foreign key from the privileges to the actual table, and then it depends on default behavior of your database, but you can have like on delete cascade, and they'll go. They'll stay, okay. That may be true, okay. But the point here is that we can ensure the integrity of the privileges and then the actual data. So we can make sure that the rules for granting access to data and how you access the data and the actual data keep the same, yeah. If we look at the Hadoop world at the moment, and this is Apache Sentry, which is Cloudera's project. You may be familiar with Ranger, Apache Rangers, Hortonworks. You know, Cloudera always have one thing and Hortonworks always have another. But they're pretty much the same principle. What they're doing is they're trying to centralize all access control in a service, and the service will have a database underneath it. And you'll put all your policies in here. And you'll have audit trail as well for accessing policies. So anytime you access HDFS, the idea is that you check with Sentry, do you have the authorization to do so? Impala, the same thing, Solar, Hive, etc. So this is, you know, if you're just thinking of this in terms of scalability, this is going to be a big bottleneck. Yeah, everything's going to go in there and out again. So one of the issues you have here, though, is what happens to the policies if I update the data? And what happens to the data if I update the policies? I mean, how do we keep these two in sync? How do we maintain the integrity of the data and the policies? Okay. Any ideas? Because I don't know, really. I really don't know how you do it. The other thing to notice here is we have these things called caches here, right? So, like I mentioned, this is going to be a big bottleneck Sentry for you. You're not going to be able to handle all of the operations on your name node and Impala and so on. So what they suggest is caching the policies at the services. Now, the problem with this is that the policies can be quite complex, right? You have this policy editor in Sentry, I think it's called Hue, sorry. And this is how you specify policies for Cloudera. And you can see here you have like, you know, I have a role and then I specify some privileges for that role. I can define groups and add users to groups and so on. And it's all quite sysadmin-like in behavior. And the real issue here is the throughput. So I don't have any performance figures for Sentry, but here's performance figures for XACML, which is the most widely used of these policy enforcement engines. Roughly, you're looking at about 2,000 ops per second. That's I think that's with a relational database backend. So it's not exactly high performance. And here's the bottom line, right? If you have policy enforcement engines and you're trying to do attribute-based access control, which is what they're trying to do ultimately, you're not going to get very high throughput. But the services like Impala and your file system underneath it are going to be able to handle a hell of a lot more. So I don't know how those two come together. Okay, so what we're doing at Hopsworks is we have a scalable security solution to handle that problem. But first I'll just introduce the abstractions that we have. So what we have is we don't have explicit privileges. So you don't define privileges, we just have a fixed set of privileges. But what we have are users, data sets, and projects. And users are basically individuals, identity. You have an email to identify yourself. We have data sets as first-class entities. And all a project is a grouping of users and data sets. So here we have project 1. It has these 2 hipster people here, and we have 2 data sets. And then we have another project here is project 2 with this little old lady and this woman here, and we have 2 data sets. And you can see that we can just draw a line around users and data sets, and that gives us a project. And that's the basic idea. The basic idea is that when we want to share data between projects, we won't copy it, we'll just link that data from one project to another. And we do it in a controlled way. Okay, so what is a user in our system? So a user is basically an account. We have, at the moment, our application supports different ways of authenticating. We have a JDBC realm. We have 2-factor authentication implemented. The application server we use supports Glassfish or Wi-Fi. They support LDAP out of the box, so that's pretty easy to add in. So all you do is you log in here, and then you're inside the system. Now the project itself, think of these as being GitHub projects. You have basically members will have a role, and the role will be either the owner of the project or a data scientist within the project. I'll tell you what the privileges are in a second, but you basically have members inside the project and then data sets. And each data set will have one project where they're a home project, and then they can be shared across projects. Okay, so what are these roles? We have 2 roles, an owner, and then we have a data scientist. So like I said already, privileges are fixed. So the privileges we have for an owner of a project is that they can import and export data. So this is something that's very important, for example, in medical studies, that you don't want anybody to be able to just download the data and go off with it on an external hard disk, or even add data to the system. The other thing they do is they manage membership. So you can see here on the left, we have a dialog for how to, it's just like GitHub, you can add a member to your system, and then they add them there. But what that's effectively doing is specifying privileges. You're saying, well, I'm adding a new user. The user will have either a data scientist or data owner role, and that person now has acquired privileges in the system. But what we've done is we've delegated the responsibility for managing privileges to users. So if you look at Sentry, in Hue, it's going to be a sysadmin who's going to be adding privileges there. So if you want to add someone to your project in Hue, you send a mail to your sysadmin and say, please add this person to my project, and they'll add them, and then you get the mail back. But in our case, it is the person who creates the project is the person who can manage the membership. It's just the same as GitHub. Now, what is a data scientist for us? Well, a data scientist is somebody who can do analytics, so write code, run code, and also request access to data sets. The owners are the only people who can actually share the data sets and explicitly have the authorization to do so. Okay, so sharing a data set is basically just selecting your data set, finding a project you want to share with, and then just pressing share. It's Dropbox. If you're familiar with how Dropbox shares data sets, you right-click, you say share, you find an individual. But in this case, you don't share with an individual. You're sharing a data set with a project. So how is this implemented, right? So you can kind of think, okay, I've got an idea of the concepts. We have projects, data sets, and users. And how the hell do you do access control in this model? Well, what we do is we have this convention for the data for the directory structure in HDFS. We have our root folder here, projects, and when I create a project, what it's going to do is going to create a directory under projects. So it's a flat namespace here, and then the data sets will be again in a flat namespace underneath the project. And if we have a data set, for example, here that's shared from project 1 to project 2, you could maybe draw the arrow the other way. We don't actually create a symbolic link even. So in HDFS, you have no support for symbolic links. We thought about implementing it, but it isn't actually even necessary for us. So what we're doing is, when we create a project, we create a subtree, and everything under that subtree will belong to the members of that project. The owner will be the person who's able to update it, and then individual data sets, they can be read-write for the users, or they can be just read-only for the data scientist and read-write for the data owner. In terms of file system privileges, what this basically means is that when we create a new project, what we're going to do is create a new group, a Hadoop group, and we're going to add those users to that group. And the same thing is true for data sets. So when we create a new data set, we're going to create a new group and add the users for that group. And when we share a data set, we're going to add the users from the other project to that group. The reason why we can do all of this is because we've put our metadata in a database. So the metadata for the file system is in a database, and then the metadata used by our front-end application is in the same database. So we're going back to this issue of how do we guarantee the integrity of the metadata, the privileges and the rules. Well, they're all just stored in the database, and we can use foreign keys to guarantee that when we remove projects, we remove all the privileges automatically. And similarly, when we add privileges, we know that the data's there. Because, and that's the problem also in existing Hadoop. You know, you can add rules for data that isn't there because you don't always check it up until it's used. Okay, so what is this backend? I said that we put the metadata for Hadoop in a database. Well, we call our database not HDFS, but HopsFS. And we've done the same with Yarn, and we just call it Hops Yarn. Okay, so this is the file system, HopsFS. You can see here that on the left-hand side we have our web app, Hopsworks. It runs on a J2E server. So one of the nice things you'll see later on is that when you're browsing the file system, all you're doing is talking to the database, so it's really quick, right? So if you ever use the HDFS file browser, it's quite slow. You have the startup time for the JVM. It kind of, you know, it takes a while to navigate around the file system, but for us, it's fast. This is running as a Java application, so there's no startup time in launching MapReduce jobs, or Yarn jobs in our case. And you can see here that what's obviously different to existing HDFS is that these name nodes look different, right? We don't have one name node anymore, or we don't have an active standby name node. We have multiple name nodes. So that's a scale out layer. So we can add name nodes to scale out, and we can shrink them down to make it elastic if we need to. So these name nodes are actually stateless, and the state is all stored in an in-memory distributed database called NDB. So this is one of the, you may have heard of new SQL databases. So new SQL databases are very high throughput in-memory distributed databases that support transactions. One thing that we need to have here in our name node layer is we need to have one node as a leader. So one name node will have to execute the coordination operations. So replicate this block to this file because, or to this data node because another data node has crashed. And so on. So this is a scale-out architecture. We can get up to 48 nodes here. We don't really have a limit here. I mean, well, there is a limit in terms of 255 nodes in total. So what is that? 255 minus 48 is the limited number of name nodes we would have. But we've scaled it out quite a bit. We've got up to like 8 database nodes, and I'll show you some figures in a minute. And it works really well for us. So we did the same. Oh yeah, so the other point is here is our metadata and our policies are all in this database here. So we did the same for Yarn, but it's slightly different and more challenging in a way for Yarn in that Yarn has a single resource manager, and then nowadays we have a standby resource manager as well, but in our case we've distributed the resource manager. So one of the things the resource manager does is it takes heartbeats from the node managers. So if you have a very large cluster with thousands of nodes, then this scheduler has to handle and process thousands of heartbeats per second, which is quite resource intensive. So what we do is we send the heartbeats from the node managers up to the resource trackers. And the scheduler then just the state of the cluster is synchronized with the scheduler using a streaming event API from the database, and that's written in C++. So we had to get low level to get the throughput that we needed to get good performance in Yarn. Again, in our case, the metadata and policies are stored in the database. So one problem we have in terms of licensing is that Hadoop is Apache v2, and the database we're using, NDB, is GPL v2. So you may be familiar with JDBC. I guess everyone's familiar with JDBC. And JDBC solves this problem by having an API. And then you have to have an implementation of the API where it's possible to have multiple different implementations. You can have a MySQL connector, an Oracle connector, Postgres connector. And in our case, we have an abstract API for the database layer called the DAL API. But at the moment, we only have one implementation. And the implementation of that is for this NDB database. But in principle, there's other NewSQL databases like MemSQL, VoltDB maybe. I guess there's other ones out there that we haven't looked at. Most of them aren't open source, unfortunately. But in principle, you can have different implementations of that database layer. Okay, with potentially different licensing models as well. Okay, so a little bit on the performance of this backend. This is a drop-in replacement for HDFS. It's a drop-in replacement. So at the moment it's 2.4. I mean, we branched earlier than 2.4, so there's a couple of features which we don't have. So we don't have snapshots and we don't have ACLs, access control lists, but otherwise most of the stuff is there. We even have our own erasure-coded replication implementation, which isn't there yet in HDFS. So here's some of the things we can do is we can have much more metadata now in our file system than you can have in Apache HDFS. So they can really, you can get to 100, maybe 200 gigabytes of metadata on the heap of your JVM in HDFS. After that, what happens is the garbage collection times start to go up, and you get these stop the world garbage collection events, and they can pause your JVM for several seconds or longer. So there's kind of a practical limit on the size of your JVM heap at the moment, which is determined by how good your garbage collection algorithms are. So at the moment, those algorithms aren't particularly going much faster. So if you go 5 years out in time from now, the scalability of the Apache HDFS name node will be determined by how much better we get at garbage collection for the JVM. Right, so we don't know it, but we can say roughly for servers, we're going to follow Moore's law, and the cost of memory for a Moore's law or for a standard off-the-shelf server will be, whatever, 20% or 10% of what it is now. Okay, so at the moment, I know of NDB clusters up to, well, 8 terabytes, I think 6, but that data will be replicated, so this will be 4 terabytes in practice. But that's still quite a lot of data. We do have some expansion in the data size, so we don't, 100 gigabytes of memory on the JVM is not the same as 100 gigabytes in our database. We use a bit more indexes, so I think our expansion factor is about 4 or something at the moment. So, if they have a 200 gigabyte name node, we need 800 gigabytes to store the same data. But we have more indexes, so we can do more funky stuff with it if we need to. Okay, here's some figures on throughput. These experiments we did in EC2 on some beefy instances there. The green line is when we had 2 database nodes. The yellow one is when we had 4 database nodes, and the blue one is 8 database nodes. So the graphs separate after around 7 name nodes or 6 name nodes. And we didn't, we kind of ran out of money. This cost me a couple of grand, I think, to run these experiments. This is the performance of HDFS here, this red line. Yeah. So this is a workload from a large company who have a 1500 node cluster, right? 1500, I think it's 60 terabytes, or petabytes, sorry, 60 petabytes. So we took their traces from their workload, and we have then a way of just doing a benchmark against that. And this is roughly to where we got to. So this is a mix of operations. You have mostly, I think the most common operation is stat on a file, for example. Stat on a file, stat on a file. But there's a lot of get block locations, which is when you want to get the locations for the blocks in a file. There's a very small percentage of writes. I think it's like 2% or something. The one thing you'll know about, if you know anything about HDFS, you'll know that there is the semantics for writing in HDFS is that one writer is allowed to write at a time. So it's single writer concurrency semantics for HDFS. So that means that one writer will block all other concurrent clients until it's done its work. So if you have more writes in your workload, this will drop very rapidly, but it doesn't affect us because we're We don't have a global write lock. We do locking at the row level. Ultimately, it's at the kind of inode level, so either file or directory level. So if you have multiple clients writing into different subtrees, they can write in parallel in our system, but you can't in HDFS. So I should say one more caveat. For some operations, we're a bit slower. If you want to delete a big subtree, that requires a lot of round trips to the database for us, and that is going to take more time. But it's not as common an operation, I guess, as the other ones. Okay, what else can we? So we like the results. We think, oh, this is a great backend. It's high performance. It scales out. The data's in a format now where we can tinker with it. Anyone can do anything they want to with your metadata. It's in tables. It's very easy to add a new table. It's very easy to add new code to the name node. What kind of cool stuff can we do with it? And I talked already about the policies that we did and that we added for multi-tenancy. But we've done some other things as well. This is another company I won't mention, but what they tried to do originally was to manage extended metadata for the files stored in the file system. So imagine you have some file here and you want to write something about the file. Like, for example, imagine it's movies, and you said, well, here's the name of the producer, the name of the studio for the movie, the actors, and so on. You'd have a lot of metadata here, and then you'd have the file here. And maybe someone is looking for all the files made by this director. So you'd look in the database, and the database would tell you which files are in the file system. And then you can go write your analysis job. So the principle is that, in theory, you'll always access the data from the API, and things will work out well. If you have good tooling, you can do this, I guess. You'll have issues if there's failures and so on, but sysadmins can fix it. But what happened in practice here was that users kind of got tired of that API, and they just start going straight down to the data. So I'll just move this in the file system, and I'll just add this new file here. It's not added to the database. And what happens over time is then your data, metadata, and the extended metadata in the database and the actual data in the file system, they just go out, hopefully out of sync, and people stop using the database. They say, well, there's no point searching the database. I won't find anything that's in here because people stopped adding it to the database. So extended metadata is what we thought. This sounds kind of cool as a use case. So why do we do this, right? So what we decided we wanted to do is we're using Elasticsearch at the back end. So you can think of, you have your data in a database. How do you get it from Elasticsearch, from the database into Elasticsearch? Well, that's pretty easy. You've got connectors or rivers to do that, Elasticsearch. But Elasticsearch, you can define arbitrary number of indexes, and we want to have a kind of controlled access to the platform by users, and we want to control what they're searching for. So we said, okay, we'll have one index, which is when you come in and log into the system, and you're not inside a project, you're just in the system. I want to be able to search for any projects that are in here and any data sets that are in here, because that's currently a problem. There's a guy, Adam Kagawa, wrote a blog entry about, he's from Spotify, he used to work at Spotify, but he wrote a blog entry about how he challenged the CEO of Spotify to say, who is the person who's not from Sweden who listens the most to an artist from Sweden called Timbuktu? He said, I'm going to prove it's me. Okay, so then the problem he had is he said it took 2 days to find the data set, right? The data sets that he would need. The data, they have a very large cluster. So in this case, for us, it's just free text search up here, and it'll give you hits back to all the data sets that are in the system. You can have tens of millions of files, and it'll tell you the data sets and projects with that particular name. The other type of search we support is that if you're inside a project, so now you're inside a project, it's a unit of isolation, then you want to search your subtree. And in that case, you just get back files inside your particular project. And then the other one is, how do you design your extended metadata? So I want to add this metadata about movies. Well, we have a designer. So this is basically a kind of an AngularJS. It's like Trello. You can move these cards around. I can do a little demo in a minute. And then you can attach that metadata to files. And if you attach it to files, you can then enter the metadata. And then you can search on the metadata as well. So this is a way. You have two ways of entering metadata, either with this is automatically generated from the schema earlier, and then this is another one, a context menu on the right-hand side of the file browser. Okay, so what this is in total, we have a designer for metadata, a way of entering metadata. When you enter your metadata that has been designed, it's all getting stored in the database, right? So our database is this source of truth for the extended metadata. And the integrity of the metadata is guaranteed because we're using foreign keys to link it to the inodes in the file system. We export that, so we have an eventually consistent protocol for exporting the metadata to Elasticsearch, and then users can do free text search on the Elasticsearch. So the database is our source of truth, our single source of truth, and foreign keys are used to ensure the integrity of it. Okay, right. So where does Flink come into this? So if you're doing analytics on our platform, we support Flink and Zeppelin, right? So we also support batch jobs. We don't have Flink right now, but we're gonna add it. This is Spark, yeah. So we have Spark, and we have some genomics platforms like Atom and Cuneiform. Flink is next on our agenda. Like I said, Flink is one of the first class data analytics platforms we're going to support. I do not agree with supporting all 50 services that Apache and Mbari have. I don't know if you've ever used Mbari. There's a green bar with like 20 services from Uzi to Zookeeper to Squoop and so on. I think people get very confused by it, so we're kind of following the Databricks style of minimalist. You either have batch jobs or you have interactive analytics. So for interactive analytics, if you were at the Zeppelin talk yesterday, this is a Zeppelin notebook. And you can see here, these are paragraphs, and we have a little percentage sign at the top indicating whether it's Spark or Flink or SQL, Spark SQL that you're executing. But this is the primary way in which people, we expect, will interact with data in the system. On top of this, we have a number of other features. There's audit logs of things being stored. I mentioned already erasure-coded replication. You can do online upgrade of the database and Hadoop as well. And we have supported automated installation. Caramel is going to be introduced in the next talk. But basically, you can install this with like 4 clicks, the whole platform. I'll do a little demo when I'm finished, but I'll do the demo now before I get to conclusions, actually. But if you want to follow along, I think I'll do it from. I have 2 instances running. One is running on. This one's running on a virtual machine and 8 gigabytes of RAM on my machine at work, which isn't much, so it's going to be a little bit slow. And then there's another one which is running on EC2 here. So if you want to use the EC2 one, that's this one here. Let me see. Okay, I'm logged in. Okay, this is interesting. So I'm logged in as Jim Dowling here this is my virtual machine at work. Let's go back. So this is the landing page. The resolution is a bit weird, you know. It's a bit low, but it seems okay. What we have here on the right is we have these projects that I talked about. So it's kind of like, think GitHub. In GitHub, you have projects. Some of them I own, some of them maybe I'm members of. We have our search here bar at the top. When we get, if somebody shares something with me, I get messages here. And I can look at them and say, okay, you know, give somebody access to that data set. And here we have a kind of an audit log of what's happened. There is an audit log by Glassfish as well if you want more details. So let me quickly go into, I can create a new project. So the whole idea is that projects should be trivial to create, just like they are in GitHub, right? So if you're working in an organization and you want to create a project, you should just be able to go in here and Flink forward. And you can pick what services you want. I'll skip the description. And it's now created, you can see it's extremely quick. It just created a bunch of directories in HDFS, but because this is running in Java, there's no JVM startup time to worry about. So now I'm inside my project, and you can see there's 2 data sets, logs and resources by default, that are created. We'll probably have another one called results as well. And I can create new data sets. You know, I can create one called Apache, and we can add new members to the project. So we can go in here and see, okay, let's add a new member. And I can go have a look. There's an admin there. And I can pick a role for the data scientist or owner. So here we've got a data scientist. We save that. And if I go back to look here as a data scientist, I think I'm logged in here. I should then see that project appear over here. on the right-hand side. So there, Flink forward appeared. Now I'm logged in as a different user, the admin user, and now I've gained access to that project there. So if we look at Zeppelin, because we've got to jump ahead a bit here. I didn't start my interpreters, did I? No. So we leave that go. It's going to take a while to start, actually. Wait, hang on. So I'll start Flink running. Spark seems to be running. Okay, so what we did, for those of you who know Apache Zeppelin, what we did was we took the Zeppelin server. It's written in Java. It has a REST API, and we're running Java, and we have J2E, so we just re-implemented the server part on our platform. And what we have is access control. So Zeppelin doesn't give you access control. So if I take this URL we have up here, and I'm now logged in as Jim Dowling, and if I log out over here, because I was logged in already, wasn't I? And I try and go to that URL, hopefully it shouldn't work. Am I in the right one? Yeah, so it asks me to log in, right? So, because what we're doing is we have project identities and then we have session keys, and when we start the Zeppelin notebook, we've updated it to store the project ID and session key, which it uses then to authenticate itself back with the REST server. So here we have Zeppelin. Those of you who haven't seen it before, I'll just see if this is running at the moment. I had some Flink examples down at the bottom. No, they're gone. I started Flink there, so we'll have a look and see how it's going. It's running. It says it's running, okay. That means it must be running, okay. But basically, for Flink, let's see, percentage Flink. I don't know if this is correct syntax, but you just press Shift Return to run something and it prints. This is the basic idea of Apache Zeppelin, that you can write your code in these paragraphs, and you can see it worked there, so it did work, or printed out anyway too. And this is written in Markdown, and then we have another one up at the top written in Spark. So you can mix and match Spark and Flink code on the same notebook, which is great. Spark seems to be still running, so that's a good sign. Flink completed, but Spark didn't. Well, it's not a good sign for Spark, but these look much nicer if you have a better, different resolution. The kind of resolution's a bit screwed up there. Okay, what else do we have here? So data sets, yeah, I mentioned we have data sets and we can share them, so that's just, sharing is just going like this. Right click on it, share, pick a project to share with, or you can write in the name of one here, like so it can go live. And then you can pick whether it's editable or just read-only to share. I don't know if I have access, so that should, yeah. So if we go back to the other user who was here, I was logged in as Jim Dowling. Okay, that's me. So if I log in here as admin, I should see that data set appear in my LifeGene project. So that's probably the first one that's kind of hidden there. There we go. This is LifeGene. So the data set should appear here, and it does. So that's the data set here that's shared with the other one. You can see we have the project name prepended on it. So we know that it's a shared data set shared from the project Flink forward. There is a jobs interface for doing batch jobs, like I mentioned. You can define a new job. Blah. I'll make. You've never seen Atom before, but Atom is a cool. It's a framework that runs on top of Spark for doing analysis of genomic data. And you know, because we have this supported in a project, we have good support for both this and the other system called Cuneiform. But we see this as a general purpose project as well. Okay, I'm out of time, so I'm gonna finish up there and just go back to the slides because I have one more thing to say here. Some people to acknowledge. So this has been a pretty big project we've run over. We started the file system over 4 years ago, and wow, that's cool. You can use it now. I mean, it's. Okay. So one 10-second demo. Here we go. Here's how I install it. I press a button called Caramel. So Caramel is going to be introduced in the next talk. Yeah, that's out. It's out now. I mean, you can use it. So if you want to install this, you can use Caramel. I click on Load a cluster definition file. I don't know where it is. Where is it? Here. It's in here. So I load this, Hopsworks, one node, and then I press launch. And at the moment it's EC2, bare metal, Google Cloud Engine, and OpenStack, but that's kind of not merged yet. OpenStack, okay. It needs to go over and back to GitHub, so all the software is stored in GitHub. So what it's doing now is downloading all the parameters, and the resolution looks a bit sucky here, which is a pity. But yeah, all I would do is then validate my key for Amazon here, and then I press launch, and that's it. I get a stack. It'll actually give me a URL, and it's all up and running. It'll run on one machine. It'll run on 1,000 machines. I won't launch this. It's pretty easy to install. We've put a lot of effort into that. So just to conclude, this was about a new platform, Hopsworks, and one of our first-class analytics engines is Flink. And this is an open source project. Everything here is open source. We're really looking for committers. Anybody who's in research, this is the tinker-friendly Hadoop platform. There's some pick-me-ups on GitHub, but just talk to us and we get involved. Like I mentioned, there's a lot of us working on this. Here's the list of contributors we've had so far. These are active ones here, I guess, and then we have a few alumni here in Berlin. I see Peter down the back and a couple others. Yeah, so basically, do we get this? I had a finish slide here. Some like the logo zoomed in and stuff. It makes you kind of a bit dizzy. But come on, zoom in. Yes. Okay. So that's it. So questions. Thanks.